Greetings everyone, this is going to be our introduction to quantum mechanics, and we'll start off by talking a little bit about light and matter. You can notice you won't see my picture up in the corner there. If I want to just focus on the slides, or if I'm having a bad hair day, I'll just go ahead and do this. And then I'm going to split this section up into 4 different pieces, maybe if they don't start to spread out too long. So we want to get into the fundamentally quantum behavior of matter as we get to very small scales of mass and size. But first we need to talk a little bit about light. And if I just can back up a little bit and give you a little bit of history. So as you can see on the slide, light is electromagnetic radiation. It's made up of waves. All these waves have the normal variables for waves. If you've seen these before, length, height, speed, and frequency. But if we back up a little bit, there was a time when scientists were of the opinion that light was more like a particle. So when you turned on a flashlight, it was sort of shooting light particles, which were really small that you couldn't see, and that's what they were doing. They were just going like in a straight line, like you would expect like a bullet or something. And then through a couple of experiments, scientists came to say, there was a debate, whether it was light, was a wave, or a particle. And through a couple of experiments, they came to say, wait a minute, light is actually a wave. And so that was where it stood for a very long time until we got to another experiment, which made people see that light actually has particle-like properties after all. So where have we ended up? Is it a particle or a wave? Yes. But mostly you can think of it as a wave. And so we have to discuss a little bit about these variables and what they mean and what we do with all of them. Length, height, speed, and frequency. So light, white light, can actually be split up. When it goes into a prism, it actually sort of opens up or bends the different frequencies. Some of the frequencies are bent more than others, and so you can see it splits this white light into the different colors of the rainbow, kind of like what's happening when you view a rainbow by the light, small droplets of water in the atmosphere. And you can see we have, the Roy G. Biv, I think it is, right? Red, yellow, green somewhere in there, and then blue. And these different frequencies are the different pieces of visible light. The electromagnetic spectrum is actually more and bigger than that, and we'll look at that in a little bit. But first, just a couple of terms for you. Amplitude is the height of the wave. We measure that from the top, the highest point on the wave, to the lowest point on the wave, so to speak, and we call that the amplitude. If I were to draw an analogy to music, amplitude is the volume. So you can take a note that's being played or sung, and you can turn the volume up, and it doesn't actually change the frequency, which we'll get to in just a second. It just makes the amplitude bigger, makes these waves larger. You don't need to know this too much, but the units of amplitude of light are the candela. We're not going to use that very much in this class, though. Okay. Wavelength is the other fundamental property of these lights that you need to know. Wavelength is designated by this lambda. You need to know that, but you'll get used to it. And it's the distance on one point on a wave to a similar point on the next wave. The units that we normally use for these are meters. So if we measured from, say, the apex of the peak here to this next one, then that would be 1 wavelength. We could, as long as we were consistent, measure from somewhere else, like say here to here, but it's just easier to go from the peaks. So that's the wavelength. And then another important one is the frequency. So the frequency is just really a number, all right? It gets some strange units of 1/seconds, called that hertz. But the frequency would be kind of like if you were looking at waves crashing on an ocean, and you just counted how many waves you saw in a certain period of time. So it's just kind of like a counting thing, right? Where you just maybe have a stopwatch and you click it every time a wave hits. So the units end up being just 1/time, and there's just a number associated with that. This 1/time is usually 1/seconds, that would be hertz. It's also sometimes called CPS, but we don't really use that. In music, the frequency, we could make an analogy, would be kind of like the pitch, right? And in light, it would be its color. I always like to mention that, just a little small note, light and sound waves operate with subtle differences. So sound waves are actually pressure waves that sort of go out by sort of oscillating forwards and backwards, outward, and then light waves are sort of going opposite to the direction, so it's transverse to the movement of the wave. All right. So here's a nice little illustration of the two different waves. They both have a different wavelength, and therefore they both have a different frequency. We'll explain why that is in just a second. But the wavelength here, you can see this thing's kind of gotten stretched out. So the wavelength is probably around twice or 3 times as big as the wavelength down here. Again, just measuring from the same point on the wave. I have a smaller wavelength, and we can also see more waves being counted in here, right? So just count the tips here, right? So 1, 2, 3 waves here, and then you see 1, 2, 3, 4, 5, 6, 7 waves in here. All right. So how do we get that the frequency is different, right? It's not immediately obvious. Well, there's a relationship in these waves related to the speed, which is going to be important for that. So just generally speaking, the speed of a wave depends on the medium in which that wave is going. So water waves are slower than sound waves, or slower than light. But in general, with light, we're normally dealing with what we think of as just a vacuum. And the speed of light in a vacuum is 2.998 times 10 to the 8th meters per second. And we'll use this many times during this class. So I won't tell you to memorize it. You'll just eventually get it, I think. Around 3 times 10 to the 8th meters per second. That's really, really fast. One time with our son, we were trying to do an illustration for what this means. And we just wanted to see how fast we could tap on a timer. You know, the fastest we could get tapping would be the lowest time interval we could get on it. And then we would see how far light would go in that really, really short interval. So the fastest we could tap on there with the speed of light, you know, say it was something like, 0.0 seconds, light would actually go all the way across the world to China and back, and then back to China, and then back to us. So 2 round trips. And, just to give you an illustration, that's really, really fast. And, right, so this is the speed of light in a vacuum. It's remarkably constant for what we're dealing with, right? We don't always have a vacuum on Earth, but it's still pretty much the same. And so the relationship between the frequency and the wavelength is that the frequency times the wavelength, right? Remember, this lambda is the wavelength. Frequency is given by nu. Lambda and net times nu is going to equal the speed of light, which we know for light in a vacuum is 3 times 10 to the 8th meters per second. Okay, so if we have a longer wavelength, just kind of point this out to you. If I have a longer wavelength, since they're equal to a constant, that means if this is larger, then this must be smaller. Okay, whereas if I have a smaller wavelength, then the frequency must be larger, because when I multiply them, they're equal to a constant. So in other words, if I have a longer wavelength here, then I must have a higher frequency on this than this wave down here. Okay. You're going to need to know how to do calculations using this relationship. The speed of light is equal to lambda times nu. I will usually give you the speed of light. You're going to need to know how to do some conversions between different units for these. Those were given to you on some previous slides and some previous lectures. Okay. All right, so I want to take some time to work through some of these calculations. And I have 2 example problems for you. I'm going to go ahead and work through the first one, and I'll let you work through most of the second one. But a red laser pointer has a wavelength of 632.8 nanometers, okay, or nanometers. What is its frequency? So we need to know first how to convert this to meters, okay, because we're going to use the speed of light, and the speed of light is meters per second. So we need to compare apples to apples when we do that. And then we're also going to use the relationship of lambda times nu is equal to the speed of light. Okay, so a unit conversion, and then we use the relationship C is equal to lambda nu in order to find the frequency. Okay, so let me jump ahead here, and I'm going to try to use this pen function here This might be difficult for me. So we have 632.8 nanometers, and the first thing we need to do is convert that. So let me show you one way of writing out this 2, 3, 4, 5, 6, 7, 8, 9 nanometers is equal to 1 meter. Okay, that was a lot of zeros, right? And if we want to think about this, we could have written this as just 1 times 10. I'm sorry for my handwriting on this. I need to get my board back so I can write these with my hand rather than trying to do it with the mouse. We could have written this as 1 times 10 to the 9th nanometers is equal to 1 meter. All right, this will be a little bit more concise. I want to show you something else. You might also see this written out with the number on the other side. So we can do that by dividing through, and then we would get 1 nanometer is equal to 1 times 10 to the minus 9th meters. Either of these is okay. I would recommend that you just, whichever one you're comfortable with, be consistent using that. At this point, I don't really do that because whatever one I use is fine. You just need to know how you're going to use it. Well, I'm going to use this equivalence, right? This is equal to this, and so I can just put them as a ratio or a fraction, and therefore I'm just multiplying by 1. And so I would have 632.8 nanometers. Let me get rid of some of this. Okay. 632 nanometers times 1 meter divided by 1 times 10 to the 9th nanometers, right? If I set it up this way, then nanometers cancels, and I end up with 6.328 times 10 to the negative 7. Remember to put your units there, right? The only one left is meters. So this is the wavelength in meters. We need that. Sorry for my messy handwriting again. I'm ashamed, very ashamed. But we'll just go ahead and move on, and I'll get my pen function later. We need to use the relationship lambda times nu is equal to the speed of light. Remember, the speed of light is just 3 times 10 to the 8th. Or 2.998 times 10 to the 8th meters per second. And then we want to solve to find the frequency. Okay, the frequency is going to equal c divided by lambda, which is 3 times 10 to the 8th meters per second, divided by lambda, which is this number here, right? So 6.328 times 10 negative 7 meters. So one thing to look at is to make sure that your units are lining up correctly. We're trying to solve for a frequency, nu, and that means we need to get units of hertz or 1 over seconds, and that's good because that's what we got, because meters cancels here, right? You have 1 on the numerator at the top and 1 on the denominator here, and then then they cancel. So this, 3 times 10 to the 8th divided by 6.328 times 10 to the negative 7. All right, that is really just an exercise in making sure that you're using your calculator properly. And if you plug everything in, you should get, if I did everything right, 4.74 times 10 to the 14th, and that's in hertz or 1 over seconds. Okay. Alternatively, we could have written that as hertz. Okay. All right. So there's what you should have gotten for that problem. And you need to use this relationship. Lambda nu is equal to c. You also need to be comfortable with doing some of these unit conversions. All right. So for the previous problem, I'll just note something to you guys. 18 to 27 gigahertz. So you need to convert these to the wavelength ranges. So you need to convert 18 gigahertz to wavelength and then 27 gigahertz to wavelength. I'm going to let you guys do that. You also have some example problems to work from the regular notes. But let me just show you something real quick. When you're converting gigahertz, since gigahertz is larger than hertz, it really kind of works out the opposite way that we did the other one. So it works out 1 times 10 to the 9 hertz is equal to the modified unit of gigahertz. Okay. So again, we could move this to the other side by dividing through. Just want to point that out that, you know, this is larger than the base unit, and so the number starts off over here if you do it the way I'm doing it. All right. So get comfortable dealing with those unit conversions, and then you got to remember that formula, and I'll usually give you the speed of light. Okay. So the electromagnetic spectrum contains many other than just the visible portion, right? This rainbow is signifying the visible portion of the electromagnetic spectrum. All right, there's a lot more to it than that. In fact, if we look here, we can see the visible portion just makes up a tiny little segment here, so these are about meters wise between 10 to the negative 7 and 10 to the negative 5, right? Little teeny tiny band there. And we have lots of other forms of electromagnetic radiation. So if you guys ever heard, you know, say your microwave oven. Your microwave oven is using electromagnetic waves around 10 to the minus 2 meters. All right. Let's see, radio waves for your radios in your cars and such are operating over here. X-rays for for doing X-rays in the hospital and such are over here, right? So it's getting higher energy as I move this direction. Higher energy is associated with a smaller wavelength, right? You guys note that this is getting smaller in wavelength, but going higher in energy. And we'll talk about that in just a second. Visible light, you can see, goes from about 750, this is in nanometers, to about 400 nanometers. Okay, so this is a larger wavelength and smaller wavelength. So red is lower energy, and the blue and violet are higher energy. Okay. Just a couple of other things to point out. Right, your cell phone operates by communicating with a cell phone tower in about the wavelength, the microwave region of the spectrum. Okay. All right, there's a couple of others on there if you guys want to take a look through that. All right, so I mentioned this before, is that we see what we call wave-particle duality in light, and we're also going to see that in some other particles. When we're dealing with light, a lot of times we call these, when we think of them as a particle, we call these photons. So it's kind of like the photon torpedo in Star Trek, is where they got that. When it hits and it's like a particle, we call it a photon. So a single photon is going to have all of the attributes that we talked about for waves, but we think of it as a particle. Yes, I know this is a little bit confusing, but a photon is going to be thought of as a particle, but it has a wavelength and a frequency associated with it. So just think of it as a little packet of light, or a little packet of wave. All right, we got this by they first started to figure this out from the photoelectric effect, which was yet another discovery of Einstein's that he could have won a Nobel Prize for, may have for this one as well, but the photoelectric effect. Okay. So let's move on from that. We'll talk about that a little bit more later. But the energy of these photons is another formula that you need to remember. Energy given by E is equal to h nu. Remember, nu is the frequency that we talked about earlier. H is something called Planck's constant. So this is energy is just equal to a constant times the frequency. So energy is proportional to frequency. If frequency goes up, then the energy goes up. If frequency goes down, then the energy goes down on a wave. Okay? And then Planck's constant, again, I'll usually give it to you, so you don't need to worry about memorizing that. All right. Here's another practice problem for you. Calculate the energy of a photon from a laser pointer. The laser pointer operates at 632.8 nanometers, and also one from a radar gun with a frequency of 22 gigahertz. I like to use this one because this is the radar gun that police officers use. So if you want to get away from your ticket, right, find some way to jam that range. And then I give you Planck's constant. And then also the units that we have for energy are joules. Okay, joules are kilograms, meters squared per second squared. It's a compound unit there. Alright, I'm about up for time on this one, so I'll have to continue on with the light and matter introduction on the next video.